There are actually two different approaches to teaching trigonometry. One is called the unit circle approach, which is what we've been doing in this class, and the other is called the right triangle approach. And usually both techniques are taught, it's just a matter of which one's taught first. I've actually usually taught the right triangle approach, so I'm used to teaching the right triangle before teaching the unit circle. This textbook and a variety of other things have caused me to want to try to do it the other way around this time. So with that said, in the order that your textbook presents it, we have gone through most of the unit circle information, and we're now going to look at using right triangles explicitly to evaluate trigonometric functions. Most of what we're going to see in this section are things that we've already done. It's just a slightly different perspective on an old friend. So let me start with the unit circle and some axes and a generic angle. For some reason, somewhere around 60 degrees just tends to be my favorite generic angle, but it is just about 60 degrees. I'm not trying to make it exactly 60 degrees. It's just randomly an angle. I could just as easily put one in quadrant 2 or quadrant 3 or quadrant 4, or I could make it really close to the x-axis. This is just where I tend to put these. Now we've learned that x comma y is equal to cosine of t comma sine of t, where t is my angle. So I'm measuring this t, this is t radians or t degrees, and that going out to about that distance, well, exactly that distance, gives me the x coordinate, which is cosine of t, and going up to that height gives me the y coordinate, which is the sine of t. If I take part of this diagram and move it out of the circle, I end up with something that looks a little bit like this. I have a distance in the x direction, a distance in the y direction, and while this is in the circle, it's easy enough to call it r. I can label it r outside the circle as well. In our case, for the most part, that has been 1. I'm going to leave it r for now, but we'll come back to it and look at it when it's just 1 as well. Now, all I've done is taken this familiar piece of our unit circle environment and taken it out of the unit circle. I still have an x, I still have a y, and I still have a hypotenuse of a right triangle, which I've labeled r. I also still have the same angle, which is t, and notice that that is this angle here. It is not the right angle, and it is not this angle up here. It's the one down here, that if I were to place this back into the unit circle environment, this would be my x-axis. So for our purposes, for this explanation, it's this angle t that's down here on the floor next to the right angle. That's the one we're interested in. Now, it's also worth mentioning that we said we were going to define x as the cosine of our angle, cosine of t. And we were going to define y as the sine of t. Well, if I wanted to, I could say that, well, let's do this as, let's go ahead and make this the radius of my circle here, my hypotenuse. So go ahead and make that 1. And then if I wanted to, I could make this x over 1 and y over 1. And then when we look back at the diagram we have over here, looking at angle t, we can say that the sine of that angle t, the sine of this angle is y over 1. In other words, it's the length of the side opposite the angle over the length of the hypotenuse. And that's how we define sine using right triangle trigonometry. So I'll put over here that the sine of t, actually I think I'll write it as y equals the sine of t, and I'm going to write that as opposite over hypotenuse. We could do the same thing with cosine. The cosine of t is x over 1, so from the perspective of this angle, the cosine of this angle is the length of the side right next to it over the hypotenuse. The side right next to it, we call that the adjacent side. So x is how we've always defined cosine of t up to this point. We can also write that as adjacent over hypotenuse. And when I say I want the adjacent over the hypotenuse, what I mean is the length of the side adjacent. to this angle over the length of the hypotenuse. In the case of sine, I want the length of the side opposite over the length of the hypotenuse. So I'm going to get ratios of two numbers. If they're both in inches, then the inch labels will cancel each other out. Let's talk about the tangent. We know tangent as y over x. Okay, well, y is opposite. I'm going to start using some shortcuts here. Opposite over hypotenuse, and that's over x, which is adjacent over hypotenuse, and opposite over hypotenuse divided by adjacent over hypotenuse means times hypotenuse over adjacent. Those cancel, and I get opposite over adjacent. All right, let's do a really quick recap here. One way to write the sine of an angle is as the y-coordinate of the point where the terminal ray of the angle intersects the unit circle specifically. Another way to write it is as the length of the side opposite that angle in a right triangle created by dropping a vertical line down from the point and a horizontal line across to the y-axis, the side opposite that divided by the radius, okay? The opposite over the hypotenuse, the opposite over the radius of the circle, or in the case of the right triangle, without the unit circle, the opposite over the hypotenuse. Two different ways to describe the sine of t. The cosine is the same. You can either say that it's the x-coordinate in a unit circle, not necessarily in any other circle, but in a unit circle, one where the radius is 1, or you can say it's the adjacent side, the length of the adjacent side over the length of the hypotenuse. And the tangent is just sine over cosine, or y over t, so it's opposite over adjacent. Now, because we know tangent and cotangent are related, cotangent of t is just 1 over tangent of t. That means cotangent of t is going to be adjacent over opposite. Secant is 1 over cosine. So that means that's going to be hypotenuse over adjacent. We need to do a little erasing here. And cosecant is 1 over sine. So I'm going to take the sine of t and flip it over. So it's going to be hypotenuse over opposite. Now, one of the benefits here is that this is really all just very abbreviated information from what we already know. So I'm actually going to erase my unit circle here for a couple of reasons. One is that I need the space, but the other is that I don't need to take up quite so much space now to convey the same information. What I have here and what I have here are essentially the same thing. So let's erase this unit circle. And from here, or within this space, I'm going to draw a generic right triangle, I hope. Okay, there's my right angle. And I'm going to label the sides. And I like the nice, easy 3, 4, 5. This is actually not a 3, 4, 5 triangle. It's doesn't have quite the right proportions, but I'm just gonna leave it like that. It doesn't really matter. I just need a generic triangle. I'm going to label that angle t, and I'm going to find the sine of t, the cosine of t, the tangent of t, the cotangent of t, the secant of t, and the cosecant of t. And it's not as hard as it sounds. From t, the sine is the opposite over the hypotenuse. I'm going to go to the side opposite all the way across the triangle to 3, and I'm going to divide that by the length of the hypotenuse. The sine is just 3 over 5. The cosine is the side adjacent, next to. Now, this side is also next to, but this is the special side, the hypotenuse, so we don't want to mess with that. We want this other side that's next to t over the hypotenuse. So the cosine is 4 over 5. The tangent, you can get a couple of different ways. One is that you can say, well, tangent is sine over cosine, so 3 over 5 divided by 4 over 5. I'll write that down just very quickly. 3 over 5 divided by 4 over 5 is going to be 3 over 5 times the reciprocal, 5 over 4. Those cancel, and you get 3/4. Or you can go straight to the idea that tangent is equal to opposite over adjacent. Tangent is going to be opposite over adjacent, which is 3/4. You can also spot that from here. The numerators of both the sine and the cosine are the numerator and denominator of tangent because those 5s will cancel when you do this. Okay, I'll get rid of that. Now that's actually the harder part. The easy part is to find these other three functions. All I need to do is take these three functions and flip them over. I just have to make sure I'm flipping over the right function for each cofunction or for each reciprocal. The cotangent is 1 over the tangent. So if tangent is 3/4, cotangent is 4/3. Cosine and secant are related in the same way. So if cosine is 4/5, secant is 5/4. If sine is 3/5, cosecant rather is 5/3. Now, remember when I first wrote these down, way back in several sections ago, I said, write them down from here, sine, cosine, tangent, then go across and back up the other way, cotangent, secant, cosecant. And you're getting a sine and a cosine, a tangent and a cotangent, a secant and a cosecant. So that's the order that they go in. And then you also get this reciprocal relationship in your table if you write it down that way. I'm now going to erase this triangle because I want this space for something else. So I'll come back to that. Now what I'm going to do is pretend that I'm not interested in angle T, but this angle over here that I'm going to label alpha. And I'm going to look at the sine, cosine, tangent, cotangent, secant, and cosecant of angle alpha. The sine of alpha is the side opposite it, 4, over the hypotenuse, 5. 4 over 5. Cosecant will be 1 over that, or the reciprocal, so 5 over 4. Cosine. Cosine of alpha is adjacent, the side next to alpha, but not the side next to it that's the hypotenuse, the other side that's next to it. So 3 over the hypotenuse, which is 5. Cosine is 3 over 5. That means that secant will be 5 over 3. Tangent is opposite over adjacent, so 4 over 3. And therefore cotangent will be 3 over 4. Now something to notice here is that the sine and cosine values here are the same as the sine and cosine values here, but reversed. Secant and cosecant here are the same as here, but reversed. And tangent and cotangent are the same, but reversed. So what happens is if you look at the other non-right angle, you get the same values, but the cofunctions get each other's values, if that makes any sense. I don't want you to worry too much about that. It should become kind of second nature fairly quickly, and you'll have an exercise to do that deals with that. But for right now, I just kind of wanted to point it out. This exercise and this exercise, the one where we found all 6 trigonometric functions of t, and the one where we found all 6 trigonometric functions of alpha, they were just kind of a generic exercise. I'd like to do one now, and I'm not going to do the whole thing just because it's going to take a while. And again, I'm almost up at 15 minutes already. So I'm going to erase most of this part and rewrite it so that we can look at a couple of special cases. Here are a couple of special triangles. Both of them are right triangles, and we've actually met these triangles before, but I just want to point out the special values of the sides here and the very special values of the 6 trig functions in these special triangles. We'll start with the 45, 45, 90 triangle. There's the 90-degree angle, and if one of the other two angles is 45, so is the other. I've labeled one as 45 degrees and the other as pi over 4. Remember, those are equivalent. I just put them both in there so we could remember that they're equivalent. In this triangle, I've labeled 30 degrees and pi over 6 in the same angle because, here they're actually the same measurement, but here these two angles are going to be different. So that's the difference there. So back to our 45 degree triangle. If I label one of the sides of this triangle S, because it's a 45, 90, because these two angles are the same size, these two sides will be the same length, and therefore having labeled one of them S, I can label the other one S. By the Pythagorean theorem, I know that this side here will have a length of the square root of the square of the first side plus the square of the second side. If I simplify that, I get the square root of 2 copies of s squared, and I can simplify that even more to s times the square root of 2. So the length of this side here, erase my arrow, is square root of 2 times s. Where am I going to put the s? I don't really like to put it out front. I think I will. That way there's no confusion about whether it's under the square root or not. Okay, now let's take a look at the sine, cosine, tangent, etc. of a 45, 45. I need to replace my t's here with the actual value because I haven't. The previous example, I was doing a generic example. I had no idea what the size of the angle was. I did know the lengths of the sides. Here, I do know what the size of the angle is. It's pi over 4. When I have the option, I'm almost always going to work in radians because I really want you to get used to seeing radians and working with radians and getting comfortable with radians because they are by a long shot, they are more common once you get past this course. They're more common when you're working in calculus and engineering and other disciplines. You'll see radians far more frequently than you do degrees. Okay, so let's take a look at what the sine of pi over 4 is. Here's my pi over 4, and I could go from either perspective here because these are the same sides of angle. I just have one labeled in degrees and the other in radians. But let's go from here. And a sine is opposite over hypotenuse. I'm going to go s over s times root 2. And just using some scratch space here, I have s over s times root 2. If I simplify that, I get 1 over root 2. Notice that that is not 0 over root 2. Okay? S goes into s once, s goes into s once. That's a 1 in the numerator. Cosine, back to here, cosine is adjacent over hypotenuse. That gives me the same ratio, and that's the thing about 45, 45, 90 triangles is that you get the same value for both sine and cosine. So adjacent over hypotenuse is also s over s root 2, which still simplifies to 1 over root 2. Tangent is y over x, or opposite over adjacent. Or, well, this is going to be y over x, so it's 1 over the square root of 2 over 1 over the square root of 2, and any number divided by itself is 1. Now I'm going to go use the other reciprocal functions, and 1 over cotangent is 1 over tangent, so I get 1 over 1, which is 1. Secant is 1 over cosine, so I get root 2 over 1, which is just root 2, and cosecant is the same because sine and cosine are the same, so secant and cosecant will also be the same. So now we have some very specific values for sine, cosine, tangent, cotangent, secant, and cosecant of the angle pi over 4, or 45 degrees. You'll see these many times this quarter, and you hopefully you recognize them from our work in with the unit circle, because we've seen these values before. I wanted to move my table over here, but it won't really let me because I can move some things and not others. Looks like I can move that, and I can move that, and I can move one of these at a time. But I'm going to run into trouble when I try to move. There's another piece that when I try to move it, it just won't work. It tries to, oh, I get that. But it tries to move the triangle with it, and I don't want to do that. So I'm going to copy some of this information over. I want this triangle to stay where it is, so I'm going to leave that there. And the reason for that is that this table that I created for you goes with this triangle. I had it under this triangle. I think that's a little misleading. So this 45, 45, 90 triangle goes with these values. Again, we've seen these values before. This is just a slightly different perspective. I had planned to do the same thing for the 30, 60, 90 triangle. I'll make the point that this this triangle has a 90-degree angle in it, and it has a 30-degree angle in it, so the other angle has to be 60 degrees, and that is equivalent to pi over 3. So we have the radians and the degrees and the radians and the degrees here. And we're going to make this table for this triangle, but I think in the interest of time, I'm going to do it in class. Well, the bad news is that this video has gone well over 20 minutes, and I apologize for that. But the good news is that it's the only video for this section. So where previous sections were broken down into subsections, this section of your textbook was not broken down into subsections, and so there's only one video. So there you have it. This is the end of the stuff we're going to do in chapter 5. We're going to continue into chapter 6, and we'll take our first assessment, major assessments, basic skills tests, and challenge set at the end of chapter 6. So this module will have 2 chapters in it. I think it's 7 sections altogether. And then the second and third module will have 6 and 8 sections respectively, so that they all have about the same number of sections. So that's it for chapter 5, and we'll see you in chapter 6.